And hello YouTube, welcome to this video. So in this video I want to talk a little bit more about tetrahedral meshes. So the story is this, I'm using Salome to generate a mesh, and most of the time the easiest way to generate an unstructured mesh is with the use of tetrahedrons or pyramids with a triangle base. Those are tetrahedrons. So I found it that when I did a heat transfer simulations, it did give me very unstable results. Often the simulation will just crash because something was wrong. There was some numerical instability. And yes, I've encountered this problem before, especially when I did heat transfer troubleshooting. And usually, yeah, there might be a problem with fvSchemes. And indeed, that can often be the case. Of course, there are many problems of instability, but fvSchemes, making sure fvSchemes is right or suitable is one of the ways to eliminate what are the possible causes of instability for the simulation. Now, when I first made these videos, I didn't know what I was doing exactly. It was my learning process that I was making these videos and tweaking and experimenting with all this stuff. So yeah, now I know maybe a tiny little bit more. I'm also beginning to know. So I stumbled across this very good PowerPoint presentation by Professor Jasak. I think that's his name. This is Professor Jasak. This link is very easily available online. And who is Professor Jasak? I hope I'm pronouncing the name right. Sorry if not. But he seems to be a professor. Yeah, he's a professor at Cambridge, and he's one of the co-authors of OpenFOAM. So yeah, he is very qualified to do what he's doing. Yeah, so he basically wrote OpenFOAM, or the fundamental parts of it, and he did his PhD and stuff in Cambridge, no, not Cambridge, Imperial College, London. So prestigious school. So he knows what he is doing. Okay, and yeah. So anyway, Professor Jasak has Jasak. I'm not don't know whether I'm pronouncing it right. Yeah, he has done OpenFOAM workshops before, so do check him out. And what's he saying in these slides? Right? Some finite volume discretization best practices. So this is from TFD Chalmers. And you scroll all the way to the bottom, you'll find, okay, tetrahedral meshes. Okay, tetrahedral meshes, these are some of the recommended finite volume schemes. For gradient, use leastSquares. Convection, use upwind. Yeah, use upwinding. And diffusion, use these things called non-orthogonality limiters. Now, when I first started, hey, switching to these schemes, I also don't know what I'm doing. I just follow these recommendations. So I assume that yes, follow these recommendations. It's established in literature. It should probably work. And thankfully, thank God it did. So credit to him for making my simulation work. But of course, I was stuck with wondering, well, what's gradient scheme? What is this convection scheme, and what are diffusion schemes talking about? So, it's always good to dig a little bit deeper, and I don't know whether I have time to actually go and explore these things one by one mathematically. Okay, but yeah, it's good to understand there are lots of resources here. Okay, so just to give a quick overview and idea, and also to point you to resources where you can find more information about what these schemes are. I'm just going to quickly go through some other videos what other people have already posted, and they are probably way more experienced, way better than I am. Yeah, but I just want to point you in that direction so that you can work better with tetrahedral meshes. Okay, so yeah, so first things first, let's shed some light on what are gradient schemes, convection schemes, and diffusion schemes. Now, I may be not the most experienced, but the consensus, the idea I get, and if you look in the CFD textbook, it's more or less that case. The idea of fvSchemes is to convert these Navier-Stokes equations, these differential equations, into matrix equations. Okay, into matrix equations. So you have this little nablas down here, which are basically the gradients, divergence, so on and so forth. These nablas, they do not exist. You know, they don't exist unless you kind of guess their values, right? The only thing in a finite volume mesh which you have are the values of, let's say, velocity, pressure, all throughout the whole mesh, and sometimes density as well. For heat transfer, you have temperature or the enthalpy. You have these values. You do not store the gradients of these values necessarily. Right? You don't store the gradients of these values. Instead, you actually you actually guess them from whatever you have in the mesh. So these gradient schemes, they are talking about this little nabla and nabla right here. This is the del by del x, del by del y, del by del z. And you can see this is the meaning. You can look at this part saying the meaning of each term. You have the del u, del t part here. This what will be, you know, you have to use a time scheme, which is usually Euler, to discretize it. That's the divergence scheme. Okay, the divergence scheme. Okay, because you have the del dot thingy down here. So this one talks about advection. You know, how is momentum carried, or how is some scalar carried. If you instead of talking about momentum transport, you talk about heat transport, right? Then you'll be carrying around enthalpy and stuff. So this divergence term is basically advection. So this is the convection scheme here. This is actually referring to divergence, because this is, you know, how these scalars, okay, the scalar being the temperature, or you can be transporting momentum as well. How this momentum is being transported from one cell to another via flow. Okay, that is actually due to convection. So this is what convection schemes are. So this is the gradient scheme, which can be an internal source, which sometimes is a conduction term. Yeah. Wait, no, it's not a conduction term. Pardon me. So this is a source term. This is a source term, and this source term, like for example, this pressure here, which can become a source term for momentum, pressure difference, pressure gradient, it will drive momentum flow, right? So these are the gradients that we are talking about right here. Okay, this is what gradients are talking about. What is diffusion? What is diffusion right here? So diffusion, yeah, like I said earlier, you probably have thermal conduction. If you look at the thermal conduction equation, yeah, you have Q equals K nabla T. This is Fourier's law. Okay. Yeah, so you have things like this: del squared, del 2t, del x squared, del 2t, del y squared, del 2t, del z squared. This is actually what do you call that? This is the diffusion. You're actually diffusing temperature. So whenever you see the del square x, del 2t del x square, or even here in the Navier-Stokes equations, you have this del 2u, okay, or nabla 2u. This is actually diffusion. So you are diffusing momentum, right? And in the heat conduction case, you are diffusing temperature. So this is why we call it the diffusion term. They have the term that sort of represents like Fick's law, that kind of form. Right, so that's diffusion scheme right here. Okay, so at least we know now what are gradient schemes, what are convection schemes, what are diffusion schemes. What are they talking about? Okay, so what are some of the useful videos I want to introduce you to learning more about this scheme? Okay, one of them is, again, you have people like Dr. Aiden right here. He has a very good, very detailed video of what a least-squares gradient scheme is. Okay, so in that video, actually, yeah, least-square gradient scheme is one of the most so-called advanced schemes for OpenFOAM. You don't always use it, right? If you go to foam, if you go to tutorial here, and I bring you to something like incompressible isofoam, yeah, and I go to elbow, I go nVim system, fvSchemes. Yeah. You go to fvSchemes and then you look at something like gradient schemes, you'll see something like what? Gauss linear. Okay, Gauss linear is a very, okay, Gauss schemes in general. They are the fundamental, almost building block of all finite volume because it relies on divergence theorem or Gauss theorem. And that should be like the foundation before we learn any other scheme. Okay, this is the most commonly talked about scheme. And again, don't have time to explain it all in this video, but okay, this Dr. Aiden explains it very well. So go to his channel, check it out. He's very good. Right. So this leastSquares method, you should know the Gauss theorem first before you start into this method, because Gauss is where we all start with finite volume. And leastSquares is a variation which estimates that gradient scheme or discretizes that gradient scheme, not based on Gauss schemes. And then what else do we need to learn? Okay, convection scheme. Okay, use upwinding. All right. So again, for upwinding, we usually talk about well, we don't use Gauss linear anymore. We use Gauss upwind. If we look at the OpenFOAM right here, you'll see divergence schemes. See, divergence schemes. We will have upwind schemes, linear upwind divergence schemes right here. So upwind divergence schemes, first and foremost, just learn the Gauss theorem first. And I'm not jumping into Gauss theorem now. You can actually look at some other videos on YouTube. Those are very common, so I'm not going to introduce so much here. The leastSquares one was a little bit harder to find. That's why I have to really point that out. So learn Gauss theorem first before you start learning leastSquares. Learn Gauss theorem first before you know what upwind is about. Okay, this interpolation scheme is also pretty important. You will find that in the course of doing your Gauss theorem, you are, since we are talking about Gauss theorem, in the course of doing your Gauss theorem here, you will actually find that there are other things inside to interpolate, because you need to find the value of whatever you're finding. Let's say your temperature or your temperature gradient. You need to find all these values at the surface. Then you can do your approximate surface integral. So I'm really going through fast here. I'm not going to explain so much, but yeah, you need the values at the surface. So, and the only thing you know are the values at the cells. And I don't have time to draw this right now, but yeah, that the interpolation comes in there. Now, probably, well, I can't promise you anything, but if I do get to it, I do get to it. But just know that the interpolation comes from, why interpolation is needed comes from this term right here. All right. So we'll place a bookmark here, and yeah, you can go YouTube and find more videos or find more things, but I'm just pointing you in that direction. Okay, so yeah, so and then upwinding and everything all comes from here. Interpolation comes from there, and then you can look at other videos for upwinding. Okay, so and then last thing I want to touch on are these things called non-orthogonality limiters. So remember just now, we have the diffusion schemes being like this. Okay, the nabla square thing, which actually talks about that so-called diffusion term. So if you take a look at this thing here, it's a very generalized diffusion looking term. So it's del dot. This is a gamma right here. This says here gamma, the diffusion coefficient. So that diffusion coefficient in momentum, it will be the kinematic viscosity usually. In temperature or thermal heat transport, this diffusion coefficient will be thermal conductivity. In mass transport, when you talk about diffusion and concentration, this will then be the diffusion coefficient, the actual diffusion coefficient that you have there. Right, so this is the diffusion term. Okay, so this diffusion term can be broken down into two parts. And you can see that inside here there is a gradient first. Okay, there's a gradient that you need to so-called interpolate. Okay, so there's this gradient term right here. So that's why you have this SN gradient. Okay, SN stands for surface normal. Okay, So there'll be a gradient scheme. So you need to know your gradient schemes well first. After the gradient scheme, you actually notice that if you look at this thing here, this is actually a vector. Okay, this is actually a vector, and you are performing divergence on a vector. So you need to know your divergence schemes well as well. So some of your other Gauss theorems will come back here, most definitely. You can see this Gauss is here again. Why is there a Gauss here? This Gauss here is meant to transform this divergence, okay, this divergence term into a so-called surface normal integral or surface integral term. Okay, and then you can do your whatever discretization from there. Okay, so I'm just pointing you in the direction there. I'm not going to explain. It will take many videos to explain in a very easy to understand way. I don't exactly have the time to do that at this moment. Yeah, but all right. So okay, what are limiters, right? What are limiters? So where can you find resources to tell you more about limiters? All right. So okay, so limiters usually come when you're talking about gradients. Okay, you have this limiter right here. It says limited surface normal gradient scheme. You probably want to take one of these. So this is where the limiter comes in. Okay, these are surface normal gradient schemes, and just remember this Laplacian scheme here is actually a combination of two schemes. You're actually having a gradient scheme here because you are discretizing this gradient, and then you have interpolation schemes because you need again to do this gradient thingy here. All right, but you also have this what do you call it, divergence. Okay, divergence, the del dot operator here. So the limiter actually falls under more or less under here, this surface normal gradient scheme. Okay. Okay, so all right, it's getting late for me. So I guess this this MIT lecture by Aerodynamic CFD of the flux limiter. Okay, these are actually good videos. I can actually share the link. So this actually give you some sort of idea as to what limiters are, okay, why they are handy, how they can help you to do stability, help you increase your chances of having a better, more stable solution. So yeah, I'll leave those in the link. Okay, I won't say this is meant for slow and steady learning where things, you know, are guaranteed to be explained nicely, but the content is there, and actually he draws out those diagrams for you so that you can see what fluxes are being limited, are not limited, are being drawn, how the limiter function works in a more visual way. All right, so these two are good places to start if you don't have anywhere else. Of course, wolf dynamics is another one, but I think if you want to talk about limiters, these two videos are perfect, and I'll leave the link in the description, so not to worry. Yeah, and I think, yeah, that's all I have. Just wanted to introduce these resources. I have so many pages open now, so let me just go through them quickly again. Right, so we know what gradient schemes are, convection schemes are, diffusion schemes are. We can look with reference into the Navier-Stokes equations. And of course, we can look at the OpenFOAM documentation itself to see which terms they're talking about. So Laplacian schemes, divergence, gradients, so on and so forth, and interpolation. Okay, so this particular document is by Professor Jasak from Cambridge Department of Physics. Okay, and of course, so we know what are the basics we need to do. We know what each of these schemes are. We know what the foundation of a finite volume discretization. It all most of them boil down to the divergence theorem, which is over here. You can actually look at the Wolfram one as well. It's a more mathematically digestible way of looking at the divergence theorem rather than, you know, this triple integral that looks so scary. Okay, you can talk about gradient schemes, least-square schemes by Dr. Aiden right here. Okay, here's another paper that talks about least-squares, but it's more how do you say, lengthy paper, more verbose, and it's actually more involved. So if you want a quick introduction, this is not for you, but it's here. Here's another paper on the leastSquares schemes from NASA. You can go and take a look. I'll leave the link in the description. And of course, if you want to look more about Professor Jasak, here is an OpenFOAM workshop for you. All right. This is just to show you the Laplacian or the diffusion term. This should go pretty early on, right here. Okay. Then after that, we talk about leastSquares gradient, again Dr. Aiden's channel, or even there's a upwind schemes here. So you can go and watch those videos if you're interested. Hopefully they are still up by the time I post, by the time you watch this video. And of course, for limiter schemes, you can actually look at these two videos here just to start off your learning journey. Okay. So I don't have time to make my own video series right now, but I'm just leaving this here to point you to good resources where you can start learning about fvSchemes a little bit more in detail. And hopefully you get a better solution with tetrahedral meshes. And yeah. Well, I'll see you again. Bye bye.